Hi everyone, my name is Jordan Thorpe and this is my EE5183 Nano Focus presentation. My topic today is radiation effects on semiconductor devices and the selection of architectures, processes, and materials that can be used to help mitigate them. While there are various hardening methods out there, my focus today will be on the techniques used during IC design and fabrication. So before I get into the radiation hardening methods I've studied, I need to lay some groundwork. So we're going to go briefly over some of the radiation sources and types that we encounter, as well as the radiation effects on semiconductors. And those can be broken down into your total ionizing dose, TID, transient dose effects, and your single event effects, or SEE. Then we'll look briefly at the challenge of developing radiation hardened devices, and we'll look at the physical radiation hardening techniques, your material selection, process control, and design architecture. And then we'll finish up by taking a look at the cutting edge and future research that's going on right now. And we'll conclude with a summary of the highlights. So to start off, the radiation sources that we have to be aware of can be broken down into two categories. We have our natural space environments, which consist of, like, for example, your Van Allen radiation belts, shown here in this image, is where the trapped particles arrow is pointing. It's where the charged particles get trapped in the magnetic field of the Earth, and they consist primarily of protons and heavy ions. Cosmic rays from outside our solar system and solar flares also fall under this category. Two of the most well-known sources of man-made radiation are the nuclear reactors, shown on the right, and the nuclear weapons, shown on the left. Those sources are primarily comprised of gamma rays, X-rays, and neutrons. So obviously not a comprehensive list, but gives an idea of some of the sources that we have to deal with. So radiation can affect electronics in a number of different ways. On this slide I've broken it down into three damage mechanisms: your lattice displacement damage, or also known as your non-ionizing energy loss, NIEL. Your ionization effects can be further broken down into total ionizing dose, TID, which is a low dose rate over an extended period of time, or your transient dose effects, which is a higher dose rate for a shorter period of time, and your single event effects. And those can get broken down into a number of different effects that we'll briefly look at in a minute. And then finally there's your nuclear reactions, which are interactions between a silicon atom and neutrons and protons, which create secondary particles, which then create more lattice displacement damage or ionization effects. We're not going to look at nuclear reactions much in this presentation, but just so you're aware. Alright, lattice displacement damage occurs when neutrons, protons, and heavy ions, heavy particles, or high energy gammas collide with atoms in a crystal lattice. So it's best illustrated by this illustration here on the bottom. You can see the incident neutron. It comes into the lattice structure. It knocks an atom out of place. That atom then comes to rest between other atoms and their bonds, and that's where your interstitial atoms come from. It leaves vacancies where the atom was, and that then creates a place for positive charge to get trapped. So there's those trapping centers. And when this event occurs, you also get some transient electrical currents, and it also causes chemical and atomic alterations in insulators such as your gate oxide layers. Displacement damage is permanent and causes n-doped or p-doped regions to become more saturated or more depleted, as the case may be, and it increases the number of recombination centers and causes a loss of transistor gain. Alright, closer look at total ionizing dose. This classification of radiation is a concern for long missions in space and for electronics near nuclear reactors, for example. Basically anything that's in the constant presence of radiation. So some of the sources are electrons, protons, heavy ions. Common source is photons, and when the photons are incident upon a material, for example an insulation oxide, their energy is high enough to create electron hole pairs. Photocurrents are induced when the electron is swept away due to its higher mobility. So if you recall from quantum mechanics, the energy from a photon can cause an electron to jump from the valence band into the conduction band, and in the case of FETs, the electron gets whisked away by the electric field. That then leaves more holes than electrons or a positive charge in your oxide layer. The holes end up trapped in the insulator, and TID is also caused when high energy electrons traveling at high velocities knock other electrons out of their bonds, leaving holes as well. So one of the fascinating effects of total ionizing dose on FETs is that it shifts your threshold voltage due to the holes trapped in the gate oxide. So you can see down here a little image of positive charge getting trapped here in your gate oxide. That then makes your N-channel FETs harder to turn off, and your P-channel FETs harder to turn on, because there's an inherent positive charge there that either aids or works against the voltage that you apply. Also, processor speeds and throughput decreases, your open loop gains and your op amps increase bias currents, increases offset voltages and currents. So not very good with op amps. As far as memories go, you can degrade your access time, logic, propagation time increases. Your frequencies can shift in your crystal oscillators, and in terms of fiber optics, you can darken your color centers. Transient dose effects are fundamentally different from TID. I guess the main difference just lies in your dose rate. So for TID, it's a low dose rate. For transient effects, it's a high dose rate. You can kind of compare it. If you take, for example, you look at a satellite in a deep space mission, it's got a lot of low dose rate TID effects that it has to be hardened against, compared to electronics that are near a nuclear explosion that receive an alarmingly high rate of incident radiation. The flux is high dose rate, and the high radiation flux generates photocurrents any and everywhere in the semiconductor, which effects can vary widely depending on the device irradiated. It can cause random behavior in transistors, causing some to briefly open and others to briefly close for a short time. You can see how that could be a problem for things like half bridges on a switch node power supply, safety circuits, and most logic devices, among many other things. Lastly, we have single event effects. This phenomenon occurs when a single high-energy particle travels through a semiconductor, leaving an ionized trail in its wake. Single event effects are a concern for space environments, since that's where they usually occur. They're not usually destructive, but they can cause problems such as data corruption, bit flips, clock errors, false interrupts, logical state changes, things like that. And so SE effects can be categorized into many different types. We'll just briefly run through these so that you're cognizant of them. There's like single event effects, which changes your information storage, so bit flip. Single event transients, which cause errors in your combinatorial logic. Single event snapback. Single event latch up, which as you know, the latch up is due to the parasitic PN thyristor structures. You can get a latch up, which not a good thing, obviously, and it remains until power is removed or until something breaks, right? And if it does get to the point where you're getting past latch up, you can get to the point where there's a burnout, and that's when your devices are damaged beyond recovery. There's a little example down here of a burnout, so not a good thing. There's also single event gate rupture, and that's an interesting one. It's if a charged particle hits a gate oxide layer, the ionized atoms in the trail can create a path for the current to flow from the gate to the channel. And if there's high power in the channel, that can flow back up to the gate and rupture it. And this problem worsens as gate dielectrics become thinner. So your gate oxide gets thinner, it's easier for that current to flow back up and rupture your gate. And then lastly, there's your single event dielectric rupture and neutron-induced upset. Neutron-induced upset occurs when a neutron strikes a structure, causing the release of a charged particle, gamma, often, which then causes one of the effects mentioned above. Well, you made it through Radiation Effects 101. Good job. So now we're ready to look at radiation hardening. So what is it? So radiation hardening is a technique to design and test electronic components and systems to make them resistant to damage or malfunctions caused by ionizing radiation, such as particle radiation and high-energy electromagnetic radiation, which would be encountered in outer space, high-altitude flight, around nuclear reactors, or during nuclear accidents or warfare. So there are a lot of challenges with making electronics radiation hardened. First of all, it's a very niche market, primarily space, military, and nuclear power applications. Not to mention, the whole process is very expensive. There's low quantities, low demand, those drive costs up. The testing and verification is also very expensive. Also, Rad-hard integrated circuit designs rarely start with a clean slate. For the most part, you're not going to find many semiconductor factories that are wanting to open up a special line for Rad-hard manufacturing. Due to the cost and the market, there's just not much there. So most of the time, they try to save money by taking a commercial part and making tweaks here and there to harden it enough to market it as a new product. And as we're going to see, that's not an optimal game plan by any means, but it is a solution given the high cost of making these devices. So very importantly, the meaning of radiation hardened must be defined for every application. So, for example, you see these two data sheets for a couple different parts. It calls out what their radiation tolerance or hardness is. So it tells you like what dose rate they're hardened against, and you can also see some of these say, oh, it's hardened against single event latch-up or burnout. And so, but you have to realize that when it says it's rad-hard, it doesn't mean it's hardened to every type of radiation. You might have a device that's super hard against total ionizing dose, but it is very susceptible and will break immediately, right, under like single event effects. So you just have to be aware of that. And then lastly, it's an interesting observation that as our device geometries get smaller and smaller, radiation effects become less likely, which is a good thing. The probability of a charged particle hitting a nanoscale gate decreases significantly. However, if it gets hit, you can be sure that upset will occur best. So the probability of damage decreases, but severity increases. All right, so now we made it to the good stuff. So some of the techniques that we can use in terms of materials go, there's a couple different choices of substrates that are really good for hardening against single event effects. And there's your silicon on insulator and your silicon on sapphire are the two most common ones. These new substrates insulate neighboring structures from charge due to heavy ions. SOI and SOS are used to help harden against SEE effects and are resistant to latch-up due to the complete isolation of the N and P well structures. In other words, the PNP and thyristor structures discussed earlier are eliminated. Silicon on sapphire is also an excellent insulator and prevents stray currents from spreading to nearby circuits. It's also, one benefit of silicon on sapphire is that the ingot for a sapphire is created in the same way as a silicon ingot, so we know the process. It's very similar. One downside of these substrates is that they are very expensive. For example, an SOI substrate alone is about 10 to 15% of your total manufacturing cost, so quite a bit. And then just to mention, silicon on diamond is also a promising substrate due to its high thermal conductivity and insulating characteristics, but of course, as you probably are already thinking, it's very expensive, almost probably to the point of being not too realistic. So these substrates harden against SEE effects, but they don't have much of an advantage over TID. So here are a number of other materials that have been researched and experimented with in an attempt to understand their hardness to radiation environments. In general, the results have shown varying degrees of success. It is not uncommon for improved hardness in a certain environment to be accompanied by degraded hardness in another. Some of these include gate oxide implants such as aluminum, chromium, and nitrogen, dual-layer insulators with phosphosilicate glass or nitride layers, polyamide as a planarizing thin film dielectric between layers. Aluminum oxide was studied as a gate insulator and shows promise, though it has not been developed much beyond the low temp applications it's been used on. In order to use polysilicon gates, the gate oxide must be grown early in the process. As we'll see, subsequent high temperature processing steps increase the vulnerability of gate insulator to degradation of hardness. A way to reduce that risk is to use metal gate electrodes such as tungsten or tantalum. The drawback of metal electrodes is that they can lead to dose enhancement effects due to the generation of Compton electrons. These first few techniques help harden against TID effects, and then the last two here will help harden against SEE effects. Another shielding technique is to use depleted boron, which consists only of the isotope boron 11, so it's got 5 protons, 6 neutrons. If a standard boron 10 is used, cosmic radiation will produce secondary neutrons if it hits spacecraft structures. Those neutrons will then cause fission in boron 10 and produce a gamma ray, alpha particle, and lithium ion. That resulting change can then be dumped into the semiconductor structures and cause upsets. The advantage of depleted boron is that it uses a borosilicate glass passivation layer to harden semiconductor devices against SEE. Basically, depleted boron will absorb neutrons so that they don't give out secondary particles in the form of gammas, which, as we learned, is the neutron-induced upset. And lastly, the substrate itself can be irradiated with a bombardment of neutrons to reduce the gain of parasitic PNP thyristor structures to less than 1. And that defeats latch-up and burnout, which are both single-event effects. All right, next we have some different fabrication processes that can be followed to help harden semiconductors. First, the temperature used in oxide growth has a strong influence on radiation hardness. Optimum temperatures are 850 degrees C for a wet process and 1000 degrees C for a dry process. Additive gases have been studied with varying results. Argon, good choice. Nitrogen, bad choice. If the oxide is discovered to be damaged or impure, it must be stripped off and replaced, thus ensuring that the oxide is sufficiently hardened. After oxide growth, an anneal takes place to relieve stress on the silicon dioxide layer and to reduce defect density. The oxide anneal also has a specific temperature range, duration, and ambient. 850 degrees C to 950 degrees C for tens of minutes. In general, temperature should be kept as low as possible because the highest processing temperature primarily determines the hole trapping response. And then looking further, wide bandgap materials, which are defined, those are the materials defined as they have small atoms with strong electronegative atomic bonds, can give higher tolerance to deep level defects. Some examples of these are your gallium nitride, GaN, silicon carbide, and gallium arsenide. So, for example, with GaN, GaN-FET, there's no oxide layer, so they're inherently hardened against total ionizing dose, so they don't have any place to trap that positive charge. So all the techniques up to this point on this slide have been focused on TID effects. However, these last three are help mitigate against single event effects. Hardening against latch-up can be achieved by the use of a lightly doped epitaxial layer, usually less than 7 micrometers or so, on a heavily doped substrate. The low resistivity of the substrate degrades the gain of the PNP and thyristor structures, which cause the latch-up. Minimum diffusion spacings or budded contacts, where your source, from source to substrate or your well, are in close proximity. That limits the potential difference across the parasitic junctions and reduces the risk of single event latch-up. Alright, and then there's also some architectural techniques that can be used in the design phase to improve hardness. This is not a comprehensive list, but it does provide an idea as to the kinds of techniques currently used. And I mentioned earlier that it's not ideal to take a commercial design and tweak it a bit to make it more rad-hard. The reason for that is that many of these architectures that we're going to look at here are unique and generally take up more space in the layout and can't often be thrown in at the end of a design phase. So a couple of these techniques involve the shape of your transistor gates that you can use to help reduce leakage current. There are a couple different flavors, including the annular gates. Those are shown down here on the right, where the gate is circular, going all the way around your drain. There's your H-shaped gates and your T-shaped gates, shown over on the left. Your annular rings and your H-shaped gates are two types of layout design techniques that eliminate the edge leakage by removing the parasitic edge transistors between the source and the drain. They're used to mitigate TID effects on silicon. They both require more area than the standard gate, but compared to each other, the area overhead of the annular ring is larger than that of the H-gate layout. So I also mentioned earlier that silicon on insulator substrates are a great technique for mitigating SEE, but susceptible to TID. in order to mitigate your TID, your total ionizing dose, on your silicon on insulator substrate, annular or H-gate or H-shaped gates are often used. There's also a number of different architectural techniques we can use to help reduce the probability of single event latch-up. So there's basically two different types of goals that we have when we're trying to do this. There's lowering your substrate resistance and well resistance, or reducing your gain, right? So for this first one here, in order to lower those resistances, we can add more contact holes in the layout. That will reduce the parallel resistance and thus reduce the threshold voltage of the parasitic transistors. In order to reduce the gain, we should place the PMOS and NMOS transistors as far away from each other as possible. This is because the magnification factor is inversely proportional to the base thickness. So thicker the base, the smaller the gain. Or the further apart you can place your PMOS and NMOS transistors, the smaller the gain. Leakage between devices can be alleviated by surrounding every transistor with a P+ diffusion guard ring. You can see here there's the guard ring that surrounds a structure. And this forms a channel stop by locally increasing the threshold voltage of the oxide to a very high value. These types of guard rings also help mitigate single event latch-up effects in CMOS structures. Basically, they help isolate neighboring circuits as breaking up the parasitic thyristor structures that can latch up. A more involved method using guard rings, shown down here in the bottom right, is to connect your P+ diffusion ring in the P well and the N+ diffusion ring in the N well. The P+ diffusion ring in the P well gets tied to the ground, and the N+ diffusion ring in the N well gets tied to power. And that architecture is used to collect the injected minority carrier to prevent its arrival at the parasitic transistor base. So kind of an involved process, but a neat way to help harden against SEE. Trench isolation can be used to help isolate structures from one another. Basically, a trench is formed before the transistors are built up. You can have your deep trenches or a shallow trench isolation, and thus creating barriers for the leakage currents. And light guard rings break up the PMP and thyristor structures. And this last bullet about closed transistors makes reference to a technique which, from my understanding, is kind of an expansion of the guard ring principle to cover all sides of the device. And then the last architectural technique I wanted to bring up was controlling your thickness of the gate oxide. And this is a pretty simple technique, and it's a mitigation for TID effects. Basically, the thinner the gate oxide, the smaller the positive charge that can be trapped in that layer. So if you make your gate oxide really thin, then you're more hardened against total ionizing dose effects. However, we do have to be careful with making the oxide layer too thin, though, because the thinner the gate oxide, the more susceptible the device becomes to single event gate rupture. However, if you're designing for an environment where single event effects are rare or non-existent, then you probably don't care, and then making a real thin gate oxide layer is a great idea. So there's actually a lot of cool research going on in this area. I wanted to highlight 4 examples here. So this first one, there's a group out of Sogang University in South Korea where they're doing some experiments where they fabricated carbon nanotube network FETs using single-walled carbon nanotubes by an arc discharge process, and that they were purified to about 95% by thermal oxidation and chemical treatment. They took some control measurements and transfer characteristics before proton irradiation. The devices were then exposed to a proton beam, and the same characteristics were measured after irradiation. They reported that none of their devices, and they had like 26 samples, none of them exhibited any significant altered electrical changes before and after proton irradiation. They claim that because their proton beam conditions are comparable to the aerospace environment, that CNT-related devices hold promise for future space applications. Another area of research is in Rad-hard polymers and coatings that can be used for shielding applications. These materials can act sacrificially and protect materials underneath by absorbing energy deposited by the radiation, and then they degrade without affecting the host material. And this technology is focused on polymers, but can potentially be applied as a final fabrication layer to absorb incident radiation. Basically a shield over your semiconductor device. There's also some research going on in regards to radiation-induced MEMS and NEMS failures and potential hardening techniques for those. This is not a well understood field at this time and is primarily focused on devices fabricated in poly and single crystal silicon and silicon dioxide with characteristic dimensions of tens to hundreds of micrometers. So, fairly large in terms of, where we are today with nanofabrication. So far the results have not been encouraging, as many types of MEMS have shown high sensitivity to dielectric charging from ionizing radiation, including changing capacitive calibration, collapsing parallel plates, and stuck comb drives, typically due to trapped charge in dielectrics, which is a TID effect. It has also been reported that TID effects can shift the output voltage of MEMS accelerometers under proton irradiation. Lattice displacement damage is a concern for MEMS and NEMS devices since non-ionizing energy loss can alter mechanical properties and affect functionality. Some examples of vulnerable devices are RF switches or cantilevers. However, on the positive side, it does appear that MEMS-NEMS-based logic devices have the potential to be inherently resistant to transient radiation effects such as single-event effects, but follow-on research will have to be done before any such technology can ever get introduced into the market. But there's no doubt that the hardness of MEMS and NEMS will be application and device specific. And I expect as MEMS and NEMS continue to grow in popularity that we'll see a increase of study of radiation effects on such devices. And then the last one here, quantum dot devices also have inherent Rad-hard qualities due to their small size. For example, multi-quantum well or quantum dot devices can be tens or even hundreds of times more radiation tolerant than conventional bulk devices. And it has been reported that quantum dot or CNT-based photovoltaic devices were 5 orders of magnitude more resistant than the conventional bulk solar cells. Just as a summary, the radiation effects on micro and nano devices has to be taken into account as these devices continue to shrink. Radiation hardening is a complicated, expensive, challenging process. It definitely isn't a trivial pursuit. There has been and continues to be quite a bit of interest in developing techniques and methods at the IC design and fabrication level to harden devices from radiation effects. And today we just looked at the some material selection, process control, or architectures that you can use in the design. And then, of course, as we can, we're going to continue to find improved materials and processes and architectures that will allow us to harden devices for future space, military, and nuclear power applications. Thank you.